career opportunity for the future. Really, it's my personal opinion and my personal experience that it's good to be active in the IT type voluntary positions. And you know, next year Waterloo is hosting this CITE conference, so it's a great opportunity to get involved. All right, so now the topic of today: safety analyst software for efficient and effective road safety management. It's a project that our company, CIMA, did for the Ministry of Transportation Ontario. It's finished, I believe, a few days ago after almost 2 years. Relatively big undertaking. First time in Canada that this software is being used by the Ministry of Transportation. I think Alberta and Manitoba are following the MTO to have this software as part of their road safety management program. So the outline of my presentation, I will give a quick introduction why this software was developed, and then I'll talk about the capabilities of the software. And then a little bit of my experience with the projects we did for the Ministry of Transportation, MTO, and then I'll draw some conclusions at the end. You all know Highway Capacity Manual, right? When was it first published? 1965, yes. So, long time ago. And it was like 30-page document. And it evolved into a document that it's a multi-volume document right now. And some of the materials also on the web in the 2010 volume. The traffic engineers are very familiar with the Highway Capacity Manual, and practitioners have been using this manual as the Bible for all of the traffic engineering related problems. Let's look at the science of road safety. Science of road safety mostly became evident that there is another field attached to it. Safety has been always important, but the science of road safety and the connection with the statistics really started to become evident in the 80s. And then Dr. Ezra Howard from the University of Toronto was the frontier of developing science of road safety. And he has a very important book. You see it right here, this observational before and after study road safety. And it's a really Bible of before and after study in road safety. And then there were NCHRP reports and also research papers, right? It was not, the practitioners in road safety didn't have a one document like HCM that they could use in their day-to-day lives. And then what happened, AASHTO, TRB, and US DOTs, also Ministry of Transportation Ontario, and a lot of people in Ontario, because of the strong road safety background of Ontario, contributed to a document called Highway Safety Manual, right? Which is, do you guys see over here? Let me move some of the chairs, make sure that you see all of the slides. Okay. So Highway Safety Manual was produced in 2009-2010. And similar to other things that we are familiar with, like all the practitioners love to have a software to automate the procedures. You'll have HCM, you have Synchro, and HCS. Right? You have the CCG, Canadian Capacity Guide, and there is a software that the purpose is to run the CCG. In planning, you have Transcat, ME models, and all of those. So the same analogy, to automate all of the procedures in the HCM, safety analyst software was developed by the US DOT and was released by AASHTO in 2010. process. If you work in the safety environment or in any safety work, you will see this process. This is called the road safety management process. And this is the essence of highway safety manual. And the road safety analyst, all of these components were coded to automate the whole process. So it starts with network screening. What is a network screening? Can you guys tell me what network screening in road safety is? It's a very important process, decision-making process, where you look at the jurisdiction, City of Waterloo or Region of Waterloo. They have a lot of signalized intersections. They have a lot of road sections, intersections, right? But they can't go out and look at all of them annually to see if they have any problems. So this network screening process is a mathematical tool that allows you to screen all of these locations and rank them based on their safety performance, and then go and allow the jurisdiction to go and look at the top, for example, if they're all in signalized intersection, top 10 locations, because they don't have more budget to look at. So they have budget to look at the top 10 signalized intersection, top 10 and top 20 road sections, top 5 freeway sections, for example. So network screening prioritizes all of these locations in terms of their safety performance. I'll talk a little bit more about this and how the network screening would work and what are the methodologies to do a network screening. And then we go to diagnose. You have your top location, signalized intersection, and then you want to, you know there are some safety problems associated with this location, and you want to identify what the problems are, or diagnose the problem. And in the diagnosis stage, often engineers look at the collision patterns, historical collision patterns. You have a signalized intersection with a lot of rear ends, so that's a pattern. Rear end collisions. You have a signalized intersection, a lot of angle collisions. And then once you have that, then you go to a site, and there's a procedure. It's called In-Service Road Safety Review. And TAC, Transportation Association of Canada, has a guideline that for engineers to do an in-service road safety review or road safety audit. And you go to the field, look at the location to see what the problems might be, and try to create a correlation, make a correlation between traffic patterns that you identify and traffic behavior and traffic flow. And then you'll come up with some statements. So you probably, if you have a lot of rear end problems, what is the first thing that might come to mind at a signalized intersection? There you go. So it might be a very short amber period, right, at that location that causes a lot of rear ends. So that kind of thing. So then, based on these collision patterns, you better know what you need to look at this during your site visit. Or you have a lot of collisions when it's dark. So the first thing is to go and look at the illumination at the location, and things like that. So that's diagnosis. And then when you do your diagnosis, and then you need to find out some countermeasures, right? This is the next step to select your countermeasure. Based on your problem statements that I said, you have the pattern is rear end, right? So what could be solutions? And also the problem is, for example, amber is short. The countermeasure for that is pretty obvious. But if you have a lot of single motor vehicle collisions, so a lot of run off the road. So what would be the solution? You might want to add rumble strips, right, to the road, or you might want to add guide rails to the or some roadside safety devices, right? So these are the countermeasures that are familiar, and the engineer needs to have experience to know what countermeasures are more suitable for different situations. And then for one problem, you might have 10 different countermeasures, right? how can you figure out which one is the best countermeasure? Then you need to know, you need to do some economic appraisal. Consider each countermeasure can reduce your collisions, potentially can reduce your collisions. And that's the reduction of collisions is one part, and then the other component is the cost associated with those countermeasures. So you do economic appraisal to choose the best countermeasure, and then you get to the next stage, which is prioritize projects. So over here, you potentially have a B over C ratio for all of your countermeasures. Those countermeasures that are not economically viable, you put them aside. But then you will have still 5 different countermeasures that are economically viable. And if you look at a jurisdiction, they have 5 different intersections, right? 5 different intersections and 5 countermeasures for each of them, but they have $1 million. So the question is, how can they distribute this funding to maximize the safety benefit of their network? And that is the prioritization of the project. A very important step, the next step is critically important, is to evaluate the safety effectiveness of those countermeasures that you eventually implement. And a lot of jurisdictions fail to do that, or fail to do it properly. And that's the before and after studies that usually is done. So, safety analysts have created 4 different modules to all of these. And those modules are network screening module, diagnosis and countermeasure selection module, economic appraisal and priority ranking module, and countermeasure evaluation. And as I said, during network screening, it screens all of the sites. The software now screens all of your sites and can give you a ranking of all these sites, and then helps you to identify location for the next step in the process, which is diagnosis. And there are different methods in safety analysts for doing network screening. The most commonly ones that are used is referred to as basic screening or using empirical based method. I'll talk a little bit about this because it is an important methodology. And also proportional analysis using chi-square test. Who have taken 643 or 343 courses here? The Dr. Helinga. Okay. Yeah, most of you perhaps. You've seen the chi-square test there to see whether the distribution of gaps is based on the exponential distribution. Right? So exactly the same methodology is used for proportional analysis. The same chi-square test is used to, at a location, see what attributes of a collision is overrepresented. So you have one location with 5 rear ends, and you want to know whether this 5 is high or it's low. What is the distribution? How big is this 5 for that location? So it compares the distribution of rear ends with all of the other locations, similar locations. So it's the same chi-square test. Okay, let's a little bit talk about this empirical based method. And in empirical based method, to compare basically to for network screening, what we have is collisions are random events, and they fluctuate. So if you look at a slice of 3 years and of collision at a location, and these 3 years, average 3 years, may not be representative of long-term performance of that location, safety of that location. That's why the empirical based method is used to get to convert the short-term performance of safety performance of a location, and then calculate or estimate long-term collision performance of that location. I have a slide later on show some of these variations and fluctuations, and can help to better visualize and understand it. But let me show it this way. There is a phenomenon. It's called regression to the mean. Right? And regression to the mean phenomenon is an interesting phenomenon because it says if this is number of years and the location is signalized intersection, for example, if you're talking about signalized intersection, and y-axis is number of crashes per year. If you have a location like this, you have some fluctuation, and you have all of a sudden a lot of collisions happen at this location. Based on the regression to the mean phenomenon, it says if nothing has changed at that location, you're expecting that this location will have a smaller number of collisions next year, and that's called regression to the mean. So if you go and then have a slice of collisions over here for that location and calculate the average, probably average number of crashes will be here, all right? But if you wait for next year, it will come down in 2 years because of the regression to the mean phenomenon. And the overall average at this location might be something like that. Whereas if you look at the short period of time, your average will looks like something like this, and this would be the difference. That's why the empirical based method is used to basically calculate this long-term average using the shorter period of time observations or collisions. To do this, we need something like safety performance function, and this safety performance function is basically a regression model. And this regression model is for all of your signalized intersection. You go and collect your traffic volume data, your geometry, how many legs do they have, and then historical crashes. And then you plot them. You see them in this figure. So x-axis is ADT, all entering ADT to an intersection. And y-axis is collision frequency per year. So you see all of these observations. And then you fit a curve, which is usually a nonlinear curve, to these points. This curve is referred to as a regression safety performance function, which relates geometry because you create it for a full leg signalized intersection, for example. And traffic control device, it's for signalized intersection. You create the same thing for unsignalized intersection. And also traffic characteristics, traffic volume, and number of collisions. And then this is used to estimate the long-term collision frequency using the empirical based method as a location. And this is a typical safety performance function that AP Analyst requires. The number of collisions per year equals, this is not for intersections, it's for road sections. The length of the section, the constant, and ADT to an exponent. And then, once you have your SPF for a location, this is your curve, safety performance function. At a particular ADT, this is an average number of collisions that you expect from all of those similar locations, right? So if in your jurisdiction you develop your SPF for all of the signalized intersection that whose ADT is a number, you're expecting to have an average number of collisions with that. So this is your curve. For all locations at 10,000 vehicles per day, ADT, you're expecting to have 5 collisions per year. So this is an average. But each location is different because of its temporal, its own characteristics. Its particular geometries, or it's the drivers that are using that, the area that the location is operating, right? So you have the observed, because for any reason you might have an observed number of collisions for that particular intersection over here or over here, right? And then in the empirical based method, you calculate collision or the expected long-term collision for a location using the linear combination of observed and your predicted. So it becomes W multiplied by your observed plus 1 minus W multiplied by your predicted, which is the value you get from the SPF. And this becomes your long-term characteristics, or long-term collision frequency at a location. Right? And because it's linear, it's always it's a linear combination of these two. It's always in the middle. Right? And then you can rank all of your locations. Getting back to network screening, what was the purpose? Purpose was ranking. So you have all of your signals in intersection. You want to rank them. You can rank them based on expected collision frequency. Right? The other thing that you can rank them is based on this difference. Right? This is because now you see this expected collision frequency is above this curve, and you hope that if you treat that location will be improved and get to the overall average of all of the intersections in that area. So your hoping is that by treating that location at this safety performance, you can bring this location down to the curve. So this difference is called safety performance, potential for safety improvement. This difference. And you can rank the locations based on this metric. What is the problem associated with this metric? If you rank based on your PSI, or potential for safety improvement, this is your PSI. This is your predicted number. This is your long-term performance. And this is PSI, potential for safety improvement. If all of your intersections are working poorly, are operating poorly, so all of these PSIs are small. So your ranking will not be very accurate. All right. So it was a very condensed version of how network screening works. And then you go to diagnosis, I said. Safety analysts assist you with different tools, statistical tool or graphical tool, to identify a collision pattern at a location. So you get your network screening, you get the top one, go to diagnosis countermeasure selection tool. It helps you identify collision pattern. And the other tool that you have in safety analyst is it's called there are some diagnosis scenarios, and the user based on the collision patterns, different scenarios are presented to the user, and user answers questions. I'll show you a couple of them. And based on those answers you provide to the software, it gives you some potential countermeasures that you need to verify them with your site visit. Let's go to them. Okay. These are some of the tools that you can use, descriptive analysis tool you can use to identify a collision pattern. Look at this. Anybody who looks at this diagram, these are different collision impact types. So collision with a parked motor vehicle, overturn, rear. Whoever looks at it sees a big number of rear ends. So you have a pattern, a rear end pattern over here, and you have an angle pattern as well. And there are different things. And this is I hope it was clear, but this is called a collision diagram. And the collision diagram is a very interesting tool that correlates different types or different impact types of collision with their location. Right? So you see I identify a variant pattern here for an intersection, but at what approaches those rear end collisions occur. And this collision diagram helped me to see it appears that you have a whole bunch of rear end collisions over here and a whole bunch of rear end collisions over here, but not so many over here, right, for those. So it helps you identify the collision pattern. And then these are the diagnosis scenarios that I was talking about. They are usually big. They were developed based on human factors and geometric design by very experienced people in human factors and geometric design and safety, road safety. This is zoomed in this part of this flowchart. And if you look at it, you start with the algorithm. The question is, are crashes occurring on sections with shoulder edge drop-offs greater than 5 centimeters? If your answer is yes, the countermeasure is remove shoulder edge drop-offs. If the answer is no, then you go to the next level. If you don't know the answer, it asks you to do something. It's called procedure. It says, okay, if you don't know, review crash records, or visit site to observe lane width, roadside shoulder maintenance, etc. Roadside shoulder maintenance, etc. Right? So it gives you some ideas about the site before you go out and do your site visit. And it is very valuable, very helpful. Look at the other question. Are the travel lanes less than 4.75 for single lane ramps, or 3.75 for 2 or more lane ramps? This particular one was for a ramp, this diagnosis scenario, etc. By the way, safety analysts originally came with these scenarios only for intersections and for arterial roads. And then we added scenarios for ramps and for highway sections, which was a very big undertaking. The next step is the economic appraisal and priority ranking. It is very strong in that area of doing economic appraisal. Just I want to reiterate. You have now some countermeasures. You want to know whether these countermeasures are economically viable or not, right? So you do economic appraisal. It has a lot of metrics based on which you can do your countermeasure evaluation and priority ranking. One of the things that it has an optimization tool in there that you give the program some fixed budget, and based on that, fixed budget, it optimizes and identifies. It's an integer program. Identifies the countermeasures that are and need to be implemented. And the next tool is a countermeasure evaluation. Before and after studies in road safety are complex because during the before period, the idea is to compare after you implement, you compare your after period with your before period, right? But it's a very complex study because a lot of things changed during before and after, not only the countermeasure you implement. That's why you need a very solid, thorough mathematical algorithm or procedure to do this before and after study. Fortunately, it helps you simplify this before and after process. Let me give you a very quick example of why that is important. And many jurisdictions really claim a lot of things in newspapers and in television without doing a very thorough before and after study. They do a countermeasure, they implement a countermeasure, and then they go and say, okay, yeah, we reduce number of collisions of 20%. 20% is a lot. if you spend $200,000 and you reduce number of collisions by 20%, it's unbelievable. But you hear a lot of these things. This might help to better understand why before and after studies are important, and it has to be done properly. X-axis is different years, Y-axis number of crashes, and you see all of these fluctuations, right? And I talked about this long-term average over here. You implement the countermeasure, and hopefully after implementation of the countermeasure, your crash history changes, and you see different pattern, smaller numbers. Now, if you, in your before and after study, if you go and only take a small average over here and compare it with your average after, you get this big reduction of collisions. Everyone say, ooh, yeah, that's great, reduced number of collisions. Whereas you, in a before and after study, you need to remove all of the impacts of all of the other factors that impacted the study, and you've got to look at the long-term average performance before and after. And in this case, if you look at it, a much smaller reduction in number of collisions overall after implementation of that countermeasure. Fortunately, this tool allows us to do this kind of before and after study a little bit easier. And the hope is that if the jurisdiction has this tool available, they can do a better job at doing the before and after study and evaluate the countermeasures they implement at different locations. All right. So what kinds of data does this software need? The primary data that it requires infrastructure inventory data for roadway segments, for intersection and ramps. By inventory data, mean for a signalized intersection, for example, number of lanes, and whether it's signalized, unsignalized, when traffic signal was installed, and for a roadway, the length of the roadway, number of lanes of the roadway, and that kind of thing. And traffic volume. Traffic volume is in the form of ADT. For road segments, is your ADT. For intersections, is your entering ADT to the intersections. Just to be clear, what I mean by entering ADT. Right. So when we are talking about ADT of a roadway, it's volume of both directions, right? But entering ADT to an intersection is only these volumes. So the total of these volumes are entering ADT, and that's a factor in road safety. And your collision data. Believe it or not, a lot of jurisdictions in the world don't have a good inventory data, don't have any good traffic volume data and collision data. So the biggest problem that most jurisdictions have for their studies is lack of availability of data. And that's a concept that as a traffic engineer, you all need to get familiar with. Ontario is one of the better jurisdictions in the world with NAs. So then you have all of these traffic information. This shows the data flow in safety analysis, right? So these are your crash data, inventory data, and traffic volume data that is entered into a space in safety analysis, so data management. On top of that, you have a lot of other things. I talked about all of these countermeasures. So these countermeasures and the cost of these countermeasures, how much would cost to make a 1 kilometer rumble strip. This is very valuable because many jurisdictions don't have that kind of information. Collision modification factor for these countermeasures. Each countermeasure is able to reduce some types of collisions by 2%. It's called collision modification factor. This collision modification factor is also held in safety analysis in a database. those diagnostic scenarios are held into this database. Historical distributions of all of the collisions are held into another database. One of the good things about this software is that you can customize it for your own jurisdiction. By that, you have your own. You can put in your own SPFs, not the ones that come with safety analysis. You can have your own countermeasures. Your jurisdiction. Some of the countermeasures safety analysis is not done traditionally in your jurisdiction. You can remove them and add your own countermeasures, completely customizable, and that's a great thing about this product. So this information is also held somewhere else in safety analysis. It's called administration tool. So only administrator of the software is able to make any changes to your SPFs or diagnostic scenarios, your collision modification factors, etc. And then the analytical tool is going to use your data, the data management tool, which is your infrastructure in your volume and your collision data, and the information that is available in the administration tool. And different users can use analytical tools, which are network screening, diagnosis, countermeasure selection, prioritization, and economic appraisal, and the evaluation. All right. Okay, so this was a very quick overview of the capabilities of this software. Now I want to talk about my experience with Ministry of Transportation, Ontario, and what we did with the software. So you may say, okay, what was this project? You went and buy safety analyst, and then you are using it. It's much more than that. It's not like Central that you buy it and you can use it for your analysis. And see, one of the things that MTO was really wanted to do as part of the software is to provide access to its users. Usually IT projects are hard to do in any public sector environment because of all of the sensitive information that might be jurisdiction may deal with. So for the first time, we put this software in the cloud, and MTO is using the software not from their own servers. They're using their computers to get connected to the cloud and use the software from the cloud. So it was the first time that a jurisdiction was doing something of that nature, and that made this project successful. Otherwise, if we wanted to deal with all of the IT policy and challenges within the ministry, we couldn't do it. The other objective of this study was to calibrate and configure safety analysts based on the Ontario context, using the Ontario data. So we talked about the collision distributions. That these collision distributions, for example, were being used for the chi-square test that we were talking about, right? So we needed to change this distribution based on MTO data. What we needed to do, we needed to bring all the MTO data into the software, which was a big undertaking. I'll talk a little bit about that part. And develop SPFs based on MTO data. Use MTO's collision modification factors, and some of the other things. And then create instructions for the ministry of staff to use safety analysts. There are different methodologies for network screening. Which one of these methodologies MTO staff should use, and how can they interpret the results that they get from different modules of safety analysis? So that was one of the other parts of this project. Data collection was very, very intensive. We spent around 8-9 months to compile data for collisions, for traffic volume, and for infrastructure. But believe it or not, MTO doesn't know the exact number of lanes for their roadways. So That's one thing. They don't know number of legs of intersection. How many intersections do they have? They don't have this information compiled in one database. One time in 1996, they developed a system called IHIS. Over here, put it here. They have different databases. For infrastructure, they have IHIS. It says Infrastructure Highway Information System. So they did it at that time and never updated it again. So we had to go and find all the information from IHIS and then start updating it. Fortunately, we have Google Maps, right? So we had to drive all the problems with Google Maps to make sure that the information in IHIS is complete. And then we have AIS, Accident Information System. That's the database that MTO has for collision data. And then traffic volume is another story. All jurisdictions lack information about traffic volume because they're expensive to collect. And they need to have a good program in place to collect information about traffic volumes. MTO has a program to collect data, volume information data from their networks. Every year they count 1/3 of their network. And there are some algorithms in place to extrapolate those information counted each year to other locations. And those are interesting algorithms. I like that. Yeah, I've been involved in some of that. And so we got collision information from AIS. We got traffic volume data from different locations. There's a system called TVIS, Traffic Volume Information System, but it was not complete, so we went to other tools, tests, and master spreadsheets. Don't worry about these acronyms. The whole thing is that traffic volume was not in one location. You grab everything from different locations, and then the problem is that you need to a so that was a problem. We need to have a good methodology to do that. And then IHIS, do different things like Google Maps and IHIS. I talked about to compile whatever information is available and put them into Excel spreadsheet. Right? It is important to know that there are terms in this spreadsheet that are important. We can't change them. The terms that CITE Analyst is using is obviously different from internal MTO titles, right, or headings. But MTO staff do not know anything about CITE Analyst wordings or headings or fields. They understand their own. So we couldn't change them. So we compile all the information into these MTO titles, right? MTO headings. But if there was any gap, we used Google Maps to verify and supplement information, right? It's a very labor-intensive process. You are researchers. If somebody can develop a program that can automatically read Google Maps and convert them into measurement, would be a millionaire. Perhaps Google can do it. I don't know why they don't. Anyways, so some of the challenges. As I said, MTO's data fields did not match directly with CITE Analyst data fields. So we need to map them. And the input, there's input files to CITE Analyst are in a particular format. So all of these huge databases that we have for MTO now need to be reorganized and reformatted into something that is understandable by CITE Analyst. So what we did, first, we create some mapping tables. For example, CITE Analyst field is based on CASCO system for collision severity. This is an American system, US system. So K represents fatal if in your database. If you have a fatal collision, you represent it by K. C is a possible injury, but in the Ontario database, We have fatal, injury, PDO, non-reported, and other. So you see a lot of differences. And you have also another field in the MTO question database. It's called D-injury. No injury, minimal, minor, major, fatality. So we had to go and look at the definition of each of these CASCO scaling and MTO to map them together. So we created some mapping rules to map Ontario data into safety analyst data. One thing is that if we didn't want to use those diagnostic scenarios, we could simply define these CASCO the way we want it. But because we are using some of the scenarios that were developed in the safety analyst or diagnostic flowchart, these each have a meaning, and you have different countermeasures for different situations. That's why we have to do this mapping. So this update has to be done every year. Every year, new data should be entered into safety analysts. We couldn't just hand over this type of tables to MTO and say, okay, good luck, go ahead and do it. So what we did, we created a small tool, conversion tool, that reached the MTO, the Excel files with the titles or headings that are familiar with MTO, and convert them into input files for safety analysts. And this resolved a lot of issues. All of the jurisdictions in the U.S. Have this problem. It's the maintenance of the data, and nobody had done this simple thing before. And many of them have started doing something like that. Okay, so as part of this, these are snapshots from the data in safety analysts, and just wanted to give you for you to have some feeling about this software. These are subtypes. So these are the different categories of data that or intersections, road segments. They were categorized into different groups. For example, MTO. This means that this subtype is for MTO, intersection of full-leg signals, freeway in Ontario. So this is the site ID. So it shows that this site belongs to this subtype. That's the name of the route, King 9, and then it belongs to the central region. And because it's an intersection, you don't have a start at any location. And you have a number of collisions for each site. One of the greatest things that software like that brings to a jurisdiction is data integration. Nowadays, it's day of data mining. Everybody is expecting a jurisdiction, whenever they call, they answer questions quickly because they're expecting data is available in a database and somebody can run a query. And for safety purposes, you need different types of information, different data types. And if they're not integrated in one environment, it's very difficult and labor-intensive to have information about only one location. But in this software, if you have this, all data, all the data types are integrated. So you have your infrastructure data, you have your volume data, you have your collision. For example, if you click on that location, you will see this is the ID of the location. It shows you what type of intersection. It is a four-leg intersection. It is signalized. It shows you the direction, and because it's an intersection, it is Highway 9 and Memorial Avenue, Simcoe Road 49. So this is, and then you can look at your volume information, right? So, and it's interesting, this location, 2004, you had 23,000 vehicles per day, 2008, 14,000. So, interesting location for the major road. And you have the same information for the minor road. And all of your visions, by one click, and on that you can see all of your collision information as well, right? These are accident IDs. And the other attributes of the location. For each of these accident or collision records, we can see different characteristics. So this particular collision happened in July, was a property damage only, time of day. So this type of information will enable you to do a good diagnosis. And also there are different tools. All right, so to conclude, this software, as I said, it helps the Ministry of Transportation to integrate their inventory data, their traffic volume data, and their collision data into one system. And all the statistical approaches and engineering methodologies that are available in highway safety manuals have been built into this software, safety analyst software, and automate the process, which practitioners really looking forward to. And the methodologies, the safety calculations are based on the state of the art, which has been long overdue in the transportation industry. One of the things that help jurisdictions is to have a consistent methodology of evaluating their investment and their decisions. MTO has four different regional offices. Each of them are responsible for their own network, and each of them make decisions which project should be implemented. This provides consistency in the decision-making process. All of them are using the same methodology, the same numbers in Eastern region, Western region, Northeast, and Northwest region. And that is very good. They can't do favoritism towards one particular countermeasure by using different types of methodologies. Perhaps it is consistent across the board. And I think it's been very well received by MTO staff so far. They really like it, especially the countermeasure evaluation and not countermeasure evaluation, the appraisal tool that they have. They had to do all of the things that we learned during the economics course manually. They didn't have any tool to do that. So this is very refreshing for them. One of the things is that for all the ministry's projects, anybody who wants to do any operational study has to have some experience in safety analysts to get that kind of work from the ministry from now on. Thank you very much. If you have any questions, just please let me know. Sure.
What kind of output data does it generate? And you have touched on the lot of inputs the output.
That's a very good question. There are different outputs based on the different modules that you run. The safety analyst is able to provide you with different formats of reports. One is PDF, and then the other one HTML and CSV. Let me show you one quick example of reports. I should have one here. Sorry, I don't have it handy right now, but I can show you how it looks like. It's just a PDF report produced.
And what type of information are you?
For network screening, it's a table, right? It's a table that you have all of your locations and the ranking associated with those locations. If you run a diagnosis scenario, it provides you with the results of all of the calculations. For example, what was your collision pattern type identified? You select the countermeasures. Okay, what type of what was the B over C associated with each of these countermeasures, and it ranks the countermeasures. If it's a before and after study, for example, it shows you the percentage that number of collisions reduced, and also the variance associated with that average. And the reports are not very visually appealing. That's one of the drawbacks of the software. But and you can customize the report. That's another thing. It appears that they are working on it to make it more customizable. I can show you some of them if you. Sure.
Who controls the software?
AASHTO.
So AASHTO controls it, and do so for example, MTO purchases, it provide free charge, or how?
It's an annual license fee, $25,000 per year.
Okay, so and that essentially provides them with sort of a framework, and they need to continually update all the input data. And you mentioned there's some cost database. So
that's right.
You mentioned it's kind of an important part. But I suspect those costs for various countermeasures and the costs of improving safety, or the benefits, the savings of improving safety, are highly jurisdictional dependent. I mean, cost to implement the countermeasure in Northern Ontario is quite different than it might be in Central
Absolutely.
Ontario, and certainly very different than Kentucky or something else.
Definitely.
So are there databases that are, I understand you had on the thing, you know, the federal defaults, and then you have a local database.
Exactly.
So then MTO developing a local database for all the costs?
That's their objective. Right now, they're using the federal defaults for cost of countermeasures, because they don't have anything. So
Because they don't have anything else, so you're just using that, and as well for benefits? I mean,
no, benefits are. They did a study to estimate the societal cost of collisions. So they used the societal cost of collisions to convert each collision to a dollar value. And then they have their own adopted collision modification factors from the province of Ontario. So the way they estimate the benefit is, so you'll have, for example, XPDO. So collision reduction is calculated based on the number of collisions, call it X, multiplied by 1 minus CIMA. So, but the benefit, if you have 5 fatality as a location and 5 property damage only as a location, these two rates should be different. So the benefit is calculated by XPDO plus, so it's called EPDO, or equivalent to PDO, for each of these severity levels. So if you have a fatal injury, you have a weight which multiplied by X FI. So the whole thing, the total number of collisions is now converted into PDO. So this factor, this weight comes from the EPDO factor for fatal injury collisions, and then multiplied by 1 minus CMF. So these CMFs, to calculate benefit, are Ontario, or they estimated through the study in Ontario. These weights are calculated based on another study based on societal cost of collisions in Ontario. So the benefit is calculated for Ontario, but the cost component, you're absolutely right. It should be done locally but there's not enough data to find that.
And this crash modification factor is specific for countermeasure, but applies equally to each of the crash types.
Really depends. For example, if a red light camera is a collision modification, is a countermeasure that you implement, it doesn't change all of the collisions. It doesn't have any impact on, for example, side flow. It has impact on your angle collision, as well as probably your rear end collisions. So the collision modification factor is oftentimes associated with the impact type.
Okay, so you have a different crash modification factor for each type.
That's right.
But here where you're summing the benefit, you're multiplying by crash modification factor times the number of crashes of a particular consequence type.
That's right. Severity level. Yeah.
Severity level.
Exactly.
So is the crash modification factor?
That's right. That's a very good question.
Given countermeasure, is the same for each severity level?
That's a very good question. So in safety analysis, what it does, it says CMF total. It calculates based on the CMF for the impact types. Calculate the CMF total. CMF that is applicable to total number of collisions, and it is calculated by CMF for each impact type, or a particular impact type, minus 1, multiplied by percentage of that impact type in total, plus 1. That's the way it calculates the CMF total. Percentage of this impact type over total.
So in the equation above, where you have benefits equal to something like times CMF, is that CMF total?
It's CMF total, yeah.
So the implication, of course, is that CMF applies. There may be different severities associated with different impact types, but when you're summing the benefits, you're really looking at some sort of aggregate.
Exactly. This is the way safety analysis does. If I want to do it in Excel, I would do it that differently.
The whole intention is that it becomes uniform practice.
Exactly.
So,
anything else? Any questions?
but this, you said one of the things is you put this in the cloud, so only MTO staff have access to this, or do they allow consultants to gain access to it, or what?
That's the plan. So that's a good thing, because some of the parts of this road safety management process is done by MTO, like network screening.
Right.
So they do network screening, but usually they don't do diagnosis, countermeasure selects. That's the consultant part. So the plan is to provide access for the duration of the contract to the consultant, and then the consultant can go and do the analysis and then provide information.
And that adheres to the licensing agreement by
Actually allows it.
Oh, they do?
Yeah,
Okay.
exactly.
So they're not selling very many licenses then?
And they sell to each jurisdiction.
Right.
They say the license.
Each state,
Exactly.
Now, does that extend, does the region need their own? I guess the region, each road?
No. MTO pays only $25,000 per year.
But that includes only the MTO road.
That's right.
So if the region wants to use something.
Oh, region of Waterloo, yes.
Exactly. MTO region. So the regional authorities, governance, and then the city, right? You're basically saying each different.
Each level of government, their own.
Government needs their own.
Absolutely, yes.
Okay.
But based on my knowledge, only so far state DOTs in the U.S. and 3 provinces in Canada have purchased this.
Right. Seems like a pretty small amount.
Exactly.
When you think about their budgets for overall safety and the consequences of
Absolutely.
Of the
Absolutely.
construction budgets associated with countermeasures.
Mm-hmm.
I thought
There are other tools that, for example, Waterloo is using another tool. It's called TESS, Traffic Engineering software, and a number of smaller jurisdictions in Ontario are using TESS. But TESS just integrates data into one package. Doesn't do much safety analysis.
Right. It's more of a data management.
Exactly. Yeah, there are different things. Kingston using another system called Cartograph. Hamilton is using another product from the US. It's called MS2. So there are different things, but capabilities of this system is that this software is the safety capabilities. Solution.
Yeah. It seems that big chunk of this software is data, and this data is here. You collect it and probably you update it periodically. But this data can be used with all maybe ITS departments of the NTU can use the same kind of data.
Mm-hmm.
But as I realized, the process of, for example, the gaps that you had for the traffic and the stuff are done with CIMA just for this project. Is there any plan to share this data with other departments and or ask them to contribute to this?
My understanding is, I don't know about the internal discussions in TO, but I know that within each region, they have assigned a safety analyst champion that is responsible for recording all of the changes to the network to make sure that the data within the software is always up to date and it's done annual. I think it's a good step moving forward. For the traffic office, I don't know whether the traffic office is talking to the other offices within the ministry. That's a big thing. Thank you very much. Thank you all. Appreciate it. Thank you. Thanks, Greg. Thank you very much.
And we'll be in touch. And is that presentation something you can provide to Sahar to share around? Or?
Sure, absolutely. Yeah, definitely.
Yeah, something like you might want to be able to look through the slides and people who weren't here. So.
Sure, definitely. My pleasure. Thank you. All right.